Hello, welcome to Hocking College Lab 1103. This is week 4, day 1. Um, it is April 13th, the day after Easter, and we're moving on to talking about data analysis. So a big chunk of data analysis is talking about the uh, central tendency. So, what is the, if you think about the targets from our accuracy precision diagrams, there's the target and there's grouping of arrows. You're after kind of what the average of that grouping is. What's the you know if you could come up with a single shot that would be kind of describe that grouping, that's the central tendency. So if we plotted the number of times each spot is hit, and we had an infinite number of shots, we'd have a curve kind of like this one, and that central tendency would be the peak of that curve, um, which for an infinite number of shots would be where the largest number of hits is. We can't take an infinite number of shots, so we come up with some approximations for that. And those are the average or mean, which is, in a numerical sense, the sum of all the values. So if we're taking say we're weighing ourselves and we want to weigh ourselves multiple times to make sure we've got a good measurement, we'd sum up all of those measurements for our weight and then divide by the number of times we weighed ourselves, and that would be the average or the mean. If we want to be very specific, it's the arithmetic mean. There are a couple of other types, but they don't really show up in what we're doing now. We also have the median. So if we take all our measurements and arrange them in a list from the largest measurement to the lowest measurement, the median is the value that's right in the center. If we have an even number of values, so we don't have a number that's right in the center, we average the two centermost. And the mode is simply the value that appears most often. So if we had an infinite number of measurements, of course, that would be the most correct one. Okay. Another part of what we're doing with data analysis is figuring out the width of the curve. So how wide is this here? And there are a few ways to define that. The range, of course, is the largest value minus the smallest value. Then you've got the standard deviation, which is sort of like an average distance for each measurement from the mean. So it is, standard deviation is S. It is the square root of all of this, the square root of the sum of the distance from each measurement to the mean squared. And we square it so that everything's a positive number and we don't end up canceling things out and accidentally getting 0 when we've got a very large variation. And you divide that by the number of measurements minus 1. The variance is just the standard deviation squared. Those are the common measures for spread in our data. Another thing we are concerned with in data analysis is error, how to describe the error. There's a couple of common ways is the measured value minus the mean. So it's this xi minus x bar. It's measured value minus the mean. We see that that's an error right there in our standard deviation formula. We could also do that error, the measured value minus the mean, and divide that by the mean and come up with a percent error based on the mean. If the error is something that affects the mean, it's a determinant error. If it affects the width of the data, it's an indeterminate error. And that gets more valuable in, if in terms of measurements, if what we're doing affects where that mean is, it's a determinant error. If it affects how noisy our data is, it's an indeterminate error. A lot of times what you're wanting to do with method development is really affect the indeterminate error and get much more precision. Um, it's in some ways easier to correct for something that affects the mean, it, depending on several things. If we're talking about a single measurement, we're talking about an error. If we're talking about uncertainty, we're talking about the average of the errors from many measurements. So when I report a number as the concentration is 2.0 molar plus or minus 0.1, that 0.1 is the uncertainty. It's the average of errors from a lot of measurements. To come up with the uncertainty, we do something called propagating errors. It's a formal way to combine the errors from multiple measurements and report that uncertainty in our calculated final value. And I should correct how I've said this. Oops. Yeah, that's a much better phrasing. One thing we do not get away with doing, we cannot just sum up the uncertainty for each step. What we need to do varies by the mathematical operation that we're using to come up with something. So if we think about a concentration type calculation, we've got moles of solution, or sorry, moles of solute divided by molarity of solution. So let's follow my link here. Okay, so that is not open right now. And we'll just go right to the textbook. While that is loading, I'm going to get a drink. Alright, so this is section 4. It's table 4.3.1, I believe. There is this very nice table, one I wish I'd seen much earlier in my career because it compiles things very nicely here. Okay, when the page load, there we go. Now it's loaded completely. We can see these. So if we've got a multiplication, well, if we've got just a constant time, if our result is a constant times something, then our uncertainty is the constant times the uncertainty in that whatever we're working with. If we're doing addition or subtraction, it's the same thing. The uncertainty in our result is the square root of the uncertainty in one thing squared plus the uncertainty in the other thing squared. You're adding you're adding the square of the uncertainties in both cases for subtraction and addition. Multiplication and division are the same way. You've got the uncertainty divided by the magnitude of whatever it is. So, for example, in my molarity calculation, if A is my concentration and A is my moles of solute and B is my volume of solution, I have the uncertainty in my moles divided by the value for number of moles, and then I've got my uncertainty in the volume divided by the magnitude of that volume of solution. Square both of those, add them up, take the square root. That's my uncertainty and my concentration. Now my number of moles is probably another calculation, so I would calculate that uncertainty based on that calculation. So it is probably going to be a constant times constant being the molecular weight times the mass of whatever it is I've got in there. So that uncertainty is probably the output of one of these calculations up here. One of with the molecular weight times the uncertainty in my mass measurement. You can see we've got uncertainties for other logarithmic and exponential functions as well. And so if we've got some, we can build up a if we're given a formula for something like something more complex like the standard deviation formula, we could build the corresponding formula from these building blocks and calculate the uncertainty for something like that. Okay, go back to this. Book just spends some time discussing distributions, various distributions. That is something I'm not going to spend a lot of time talking about in this class. You should get a much better discussion in your statistics course. The one thing I will note is a lot of the basic statistics, basic to moderate statistics, assume your data follows a normal distribution. So one of the things you need to do is try to verify if that makes sense. Is it physically possible that the uncertainty you get, is that going to be physically possible, or are you going to have a less than zero concentration once you've got the plus or minus added in? Things like that. Just it's something to keep in mind. It won't show up in this class. It might not show up very often at all. They call it the normal distribution because it is, what things tend to normally follow. There are a couple other reasonably common distributions, though. Okay. Next, we have confidence intervals. Confidence interval is basically the chance that the real value, as in the value you would get as an average if you were doing infinite testing, is in this range. Usually you report the confidence interval for a 95% range, so if they tell you that that the value is 10.0 plus or minus 0.5, usually that's implying there's a 95% chance that your measurement corresponding any measurement would be within that range. And usually it's a multiple of the standard deviation based on the sample size and distribution. I'm sure there's some nice handy web calculators for that anymore. It used to be, back in the day, there'd be a table. You'd look up your sample size in one thing, and then sample size and distribute, and what probability range you wanted, 95, 98, 90. You rarely went down below that, and you'd come up with the multiple of how many standard deviations away that from the mean that is. A similar thing is significant testing. So if you've got two sets of values, it gives you really the chance that the values come from the same or different samples. So you generally start with the assumption that you're wrong. That so if say if I thought that these two things came from the same underlying sample set, oh, let's say, well, I'm blanking on a good explanation example at the moment. Let me pause. All right. So let's go with an example that's not related to cannabis. If we've got a couple of nuts, um, like nut and bolt type nuts, and I've got a couple of nuts from different manufacturers, same size and supposedly the same quality. I want to, I'm going to want to assume that they're similar, that they're that a 10 millimeter nut is this going to be the 10 millimeters for both of them. So I'm going to start off by assuming that they're different. That's my null hypothesis, is that they're different. And then I'm going to do the calculations to show whether or not that's correct. So again, it's 95% or 5%, depending on which way you're looking at it, is the normal cutoff point for making that decision. So if I do the calculations and I come out with there's only a 5% chance that they're different, then I say, okay, yeah, they're likely the same in terms of the size. 2 millimeters from both is equivalent. Um, if I came out with a higher than 5% chance that it could explain my results, then I can't reject that they could possibly be different and that there's more manufacturing defects in one plant than the other. Um, coming up with that calculation is somewhat more advanced. You could do it sort of based on confidence intervals. That's a little bit of a clunky way to do it. There are cleaner calculations, but we won't get farther into that. The last thing to talk about for data analysis is outliers. Is this data point good? There's a couple of common methods they go over in the book. Dixon's Q-test, you take the outlier, you subtract the value for the nearest point to it, and divide by the range. And then there's tables you can look at to see where that cutoff value is. Again, it's a 95% or 5% chance that they're depending on which way you're looking at it, that's the cutoff. Similar, slightly different method is grubs. You take the outlier, you subtract the mean, and divide by the standard deviation. It forms very similar. It's just slightly different values you use, and again, you look at a table to see. So let's look at some data briefly. Here we've got measurements from the first 8-week session. These were 5 milliliter measurements with the volumetric pipette. So let's just go over some basic things in Excel. If I type in the equal sign, that tells Excel I'm putting in a calculation. So I could say equals that plus that, and I can just select things. That I can select ranges like so, and it shows up as the first value colon the first cell colon the second cell. So this is cell A2 to cell A22. So I can do that. So there's some formulas that are handy. So sum is literally just add up all the values I put in. There's some average ones. There's a few different variations. Just plain old arithmetic mean average is that. So I tell it average, type in a percent, parenthesis, then give it the range I want to average. And there we go. That's my average value. Similarly, I've got mode. Now, you'll note down here there's some help things that pop up. So, with newer versions of Excel, there's this warning that you're looking at an old version that's available for compatibility. Since I've been using Excel for many years, that's what I tend to use on default. Okay, it looks like mode.mult is for if you're doing multiple columns at once. Mode.single is what we want for the new ones. So SNGL. Go, there's my mode. And median. Equal sign first. And there's no weird one for median. Or sorry, I should say new one, not weird one. So you can see we have very similar but slightly different numbers. They all provide insight into what that central value is. We've also got standard deviation. The old one is STDEV is what I'm used to using. Okay, so we've got stdev.s and stdev.p. One is for a sample standard deviation, and the other is trying to look at a population. So if if you think of this in terms of surveying, when people are taking polls for politics, for example, they're talking to a small number of people, and so they're talking to the sample of a larger population. So what we want here, we're only dealing with our sample. We didn't take in this case, if we took an infinite number of measurements, we'd be getting at something similar to a population measurement. There are tools, there are methods to try to say, okay, based on what my sample looks like, this is what my entire population should look like. That's not what we're interested in doing here. So we want stdev.s. So standard deviation is built in. I can't remember if range is. No. So one of the things we can do is look at the minimum, min. So I don't want to have to sort through what the minimum is. There we go. There's my minimum. And here's my maximum. Same thing. So that means I can just do difference here. That minus that is going to be my range. There we go. So let's see. I was gonna guess that's probably an outlier, right? That's quite a ways out from everything around else. That might be as well. Let's check that one first. So let's do the let's see, Dixon's Q, and grubs here. So equals that minus the one closest to it, that, and I forgot to put my parenthesis in the front. Let me fix that. Divided by range. There we go. Well, that's a fairly small number. So based on that, that's a pretty small difference, though. Let's see this one, because I think that's an outlier too. That minus, let's see, what's closest? Probably one of these. That's the next closest, right? Yeah, I don't have anything that's 0.99. Over, there we go. Okay. Now I would need to look at a table to see what the critical value is for that to see whether or not I can throw that data point out as being an outlier. Same way, that and that are probably outliers. That's probably an outlier. Let's try that one. Well, let's do the closest in of those outliers, because that's gonna, if I can reject that, I should be able to reject everything farther away from it, right? That minus what's closer in. Let's see, do I have any 4 7s? I don't have any 4 7, 4 8 6, 4 8 1. That's next closest in over the range. And as I for example, let's say I could reject that one. So delete that. I've rejected that. You see my range has dropped, and that's gone up slightly. Okay, I guess it hasn't gone up slightly. 163. No, my range has not changed. Okay. So you can see one of the problems with Dixon's Q is that it's dependent on, if I've got multiple outliers in the same direction, that kind of throws that off. Grubs gets around that by subtracting from the median instead, or sorry, mean, minus the mean over the standard deviation. And we got that minus the over standard deviation. And again, I would need to look up where the cutoff value is. And with this one, you can see as I remove one of these, the standard deviation shifted a fair amount, and that value got larger as the standard deviation got a little bit smaller. So, one of the other tests I've seen is a measure of how much removing a data point moves the standard deviation. I forget what that one's called. So those are all formal ways to look at your data and say, yes, this data point is just messed up. I've done something wrong here, and we should, there's more error in this particular data point than can be explained by noise in the system. There's something else going on here, and we should not include that data point in our analysis. Okay? Go ahead and delete this so it's ready for lecture this evening. And that's what I have. Hopefully I will see you all this evening, and if not, have a good weekend, or have a good rest of your week.